Okay, so Edge Centroid Decomp. So what is it? So it's very similar to Centroid Decomp, but it's like better in some ways and worse in some ways. But I think it's better. So what is it? So it's a way to decompose the tree. So let's say you have like a tree, like okay. Let's say you have a tree like maybe what we do is like we want to split all the edges into two sets. And so that's kind of the idea. So like for this case, we would have something like these edges would be in one set, and then like these edges would be in another set. And then you do it recursively. This is the idea. And our goal is that the two sets are as close in size as possible, so we get like even split. Yeah, and then you do it recursively. So then like maybe this is probably okay. Yeah, so then like in this tree you recurse, and it's maybe like these three edges and then these three edges, and then you keep doing it. And so I want to note that like first off, a node can be in multiple decomps. Like this node is now in like two decompositions. It's in this decomposition and it's in this one. And so you have to like keep that in mind. And then the other thing I want to say is for centroid decomp, I have this like mental model where it's like I want to basically compare them. So centroid decomp is kind of like this, where you find the centroid, and then basically you split it where you remove the centroid, and then you have all the other trees where they're all less than like n/2. Right, and the idea with this is like normal centroid. So the idea with normal centroid is like it's a way to decompose all paths of the tree. So like every path in the tree will either be like from the centroid down to some node, or it'll be like from some node through the centroid to some other node. And like this is the idea with centroid decomp. And there's like this mental model where you have like this, and then each node is in like log decomps, and that's kind of the idea. So there's a similar like mental model for edge centroid where it's like this is like normal centroid. Now for edge centroid, you have a model that's like this, and then there's like, this is kind of the model I have. It looks kind of like this, where you have two sides, like maybe side 0, side 1, and then you have like something like this maybe. And you have something similar over here, and so on. So there's a similar model for edge centroid, and so then it's the same idea. It's a way to decompose all paths of the tree. So, but there's actually a difference, which is that you don't want to consider centroid to node paths. So like what the idea is, like let's say you considered all nodes like U, V that go through the centroid. Like so there's at least one edge on either side. If you consider all like paths U, V that have at least one edge, then it turns out you don't want to consider paths that are like centroid V paths, because this path will be in a smaller decomposition. So like when you recurse on this side, there will be like another thing here, and then you'll split, and like this path will be handled in a smaller decomposition. So the idea is like for here, it's like there's like two cases. You handle paths that go through the centroid, and you handle paths that like end in the centroid. So there's like kind of two cases. But here there's only one case where it's like you only have to handle paths that go through and have one or more edge on either side. With yeah.
Is that always the case, like for every tree?
Always the case.
Okay.
And there's a way to split up the edge, like the trees, such that there's a like these are non-empty. Like these will be non-empty, unless it's a single edge tree. So actually, this is the caveat. The caveat is that you have to handle one edge paths like separately. This is the caveat. So this is actually like a downside of Edge Centroid. You have to handle these separately, and we'll see some problems where you do have to do this. But besides that, it is nice. Okay. And so now the question is like, how even can these two, like we want these two to be at, like, we ideally want them to be like size n over 2, n over 2. And so basically how close in size can these be? And the idea is that the best you can do, there's a case where it's like a star with 3 edges. This is like maybe n minus 1 over 2 over 3, n minus 1 over 3, n minus 1 over 3. So you have like a star with 3 edges, 3 like legs maybe, and the best split you can do is like this in one edge set and this in the other, as it turns out, and you get like a 1/3, 2/3 split. So it's basically a case where you cannot do better than 1/3, 2/3. And now, yeah.
Why is like a regular star graph with like?
Oh, sure.
Guys not even worse?
Because then you can just take like half and half, kind of.
Oh, okay. So you can like arbitrarily split.
Yeah. It's like you take one node, and then you can choose some subset of like edges, like some subset of trees on one side and some subset of trees on the other side. Like in the model, it's like you take one node. It turns out you want to choose a centroid, but you take one node and then you choose some subset of trees coming off on this side and like the rest on that side. And that will always be a decomp. Okay, so then to show that it's 1/3, 2/3, this is the worst case. Well, this is a worst case, but to show that you can always get as good as this, there's actually 2 cases. One is like, well, we choose the centroid. So basically these subtrees are all size n over 2. And the idea is, what if one of these subtrees has size greater than n over 3? Well, then we're done, because maybe equal. Because we could always just choose this guy as 1 and then the other guys as the other. And then the other case is this does not happen. So like, these are all less than n over 3, essentially. And in this case, what we can do is we can just greedily take like subtrees and put them in the first set until we get bigger, until the first set is bigger than like n over 3. So basically, we want to greedily take them until the size of this set is bigger than n over 3. And the idea is that the moment we are bigger than n over 3, the last guy we could have added does not make us too big. In other words, it does not make us bigger than 2n over 3. And then the rest of the guys are in the other set. And it turns out this just works. There's actually some discrepancy because it's actually not n. It's actually n minus 1. Because n is the number of nodes. So n minus 1 is the number of edges. So there's actually some like off by 1 errors in this math. But it turns out you can like brute force small trees and like it works out. So it like works. It's like fine. Okay, so this is like roughly the idea, but there might be some off by 1s here. Okay, now I will go over a problem that uses this. Okay. and we'll just see how it, yeah.
For this, like, greedy splitting you're doing, are you adding a subtree if it doesn't exceed the 2n/3 bound for the, like, first set?
Oh,
Or what are you
so
doing exactly?
this is, that's actually another way to implement it. You can actually just always add subtrees. Like in the implementation that we have in the lib, it's like you can always add subtrees until while it's less than 2/3, and it turns out that it also works. It's like slightly different, but yeah.
So do you have to like sort each, like do you have to do a sort?
You don't have to actually. It turns out you can always just like add. It turns out you can always just add subtrees greedily into the first edge set while it's less than 2/3, and then like everything else in the other set, and then that turns out to work. But for like a slightly different reason. This is more like showing that it's possible.
Oh, it's important that this is a centroid for that proof, though, isn't it?
Yes.
I think it would break if it's not.
Because if it wasn't a centroid, then you guys would be like most of the.
Yeah. You could, yeah, you could.
Yeah. So you might need
I
this.
was forgetting that it's a centroid, and all the trees are at most
Half.
Yeah, half. And so
That part
to me it didn't seem correct, but now it makes sense.
Yeah. Okay, so problem 1. Given a tree n up to 10 to the 5, we want is that for each I from 1 to n maybe, find number of paths or pairs UV, pairs of nodes, such that dist UV is I. So this might be kind of standard, but that's on purpose actually. And this is actually number of edges. Okay. So how do we do this? So this is basically centroid with FFT. But first I'll go over the centroid decomp solution. Okay. So the centroid decomp solution is kind of like something like this maybe. And then this is like the ith child. This is like U. That doesn't really matter. And the idea is that for each depth we get the count. So like, let's say we're like, this is like the prefix. And there's like, at this depth we have count 2, and then here we have count 5, 7, 5. And the idea is that, and at this depth we have 1, 2, 3, 4, something. And the idea is that we get the count, so it's like you loop over childs. This is normal centroid.
What's the count of?
Number of nodes of that depth. Yeah. So you get the number of nodes at each depth, and you basically FFT these two arrays, and that will just give you the answer. This is like
You're doing not dividing, but like you're doing multiple polynomials, right? Like
multiple polynomials. Yeah, because this is normal centroid, so there's at most k children, or there could be it's like a k-array tree. So like you loop over each child, and on the ith child, this is like ith. You basically FFT this guy with all the ones before. And that should consider all paths, like basically, because FFT kind of goes like this times this, plus this times this, plus this times this. And it like works out to be like the right answer. But there's actually, okay, there's a caveat to this, which is that you have to sort the childs by depth. Because what you could have otherwise you'll TLE, it'll blow up to n squared. Because what you could have is like the first guy could have depth like n over 2, and then you could have like n over 2 guys with depth 1. So you have like one big guy, and then you've got all these small guys. You could have something like this, and then you'll do like an n over 2 sized f of t, like n over 2 times, so it could blow up. So you have to sort by, yeah.
So could you also do like some inverse kind of thing where you take the entire total and FFT out when it's off and like subtract that for each subtree?
Oh, could you?
I think so.
What did you say?
Oh, you could.
Like you
Okay, good point.
take the entire frequency and then FFT. So like the overall pairs of those
Oh.
total and then subtract that for each subtree, like pairs within that subtree.
That is actually, I didn't know about that. Nice, thanks.
I'm confused how, because if you're multiplying each polynomial, why would this not count guys who go like dip and then dip and then dip and then dip? Like,
Oh, that would never.
Simple paths.
Simple paths, yeah. Sorry.
That
That would duplicate edges. Like it would go like
yeah,
like
why
these
would-
edges.
Yeah, why would it not count those?
The left polynomial is like a prefix sum.
Yeah.
Oh,
You're not
no, but if yeah, so if you're taking like a are you taking like a prefix product of the polynomial?
no. The answer is like separate. This is like a prefix sum of that.
Oh, okay. Yeah, that makes sense.
And is it possible to have that case that you showed where you have n over 2 things of depth 1?
Yes.
What was the formal definition of the centroid?
Like a node where all the components are size n over 2 or less.
Oh.
Okay. I think yeah, I'm pretty sure you could have it because on Library Checker they had it and actually it broke. Okay. So anyways. So then let's look at the equivalent solution on here. You have like the model looks kind of like this. So like at each depth you get the count nodes. And the idea is that it's just one FFT. So it's like a little, it's just a little simpler basically. So you like get the count, like you do DFS here, you get the count of nodes at each depth, you get the count of nodes at each depth, and you just do one FFT. And so it's like a little simpler. So it's like, I don't know. You don't have to worry about any of this stuff. There is one caveat, you have to special case like one edge paths, but there's n-1, like one edge paths. So in this case it's like not bad, but you do have to, you can't forget this. So you have to do that separately. Yeah.
And also, do you not? And then for the edge centroid decomp, you don't have to consider the root to centroid or node to centroid paths.
Correct.
So that's equal.
And you don't. So there's actually a trick where you start with a vector of like just a single element of 1, and then this, when you multiply this guy in with this, it will count the centroid path. Like there's like tricks you can do to do it easily here. Actually.
Oh, because you consider like a depth 0 or something.
Yeah, exactly. A single node at depth is 0, essentially. But okay, but here you don't do any of this, and you just have that, and it like works. Okay. So there's actually one more thing I want to say about this, which is that I was looking into some like n squared type stuff, and basically I ran the following code. Constant n is 10 to the 5, and then main. For J0, J. And then I did like an array index, array J maybe like a sum. I did a sum. Like print sum. And I ran this on Codeforce's like custom invocation or custom test. And with 10 to the 5, this ran in like 3 to 4 seconds. So this is like a 10 to the 5 squared. With pragmas. You can check that. And so I was kind of surprised that this was as low as it could be. And there's like a reasoning for this, which is like you're looping like in order, and there's like, it's kind of, if you loop in an array in order, there's like some caching or something. It like loads chunks of the array into cache or something. And it like, versus like if you looped like random indices, it'd be way slower. So I was looking at this, and with the Edge Centroid, you can actually replace FFT with like the naive. And on library checker, it passed in like 3 to 4 seconds.
Is that just AFJ or like in I kind of AFJ?
It would be, yeah. So the naive is like for I 0 up to size of like set 1, set 0. For j is 0 up to size set 1. You have like res I plus j plus equal count like 1 I times count 2. And the idea is that like this is, you're looping like increasing on j, and this is like fixed, and you're looping increasing on this. So it's like these are all cache like friendly, I guess, operations.
Optimizes out the multiplication. Fucking can't see that. Nice.
But yeah, so okay, but the idea is on library checker, this problem has like n, yeah, it has this bound. And there's actually one more thing I want to say about this, which is that if you do like Edge Centroid with like the naive multiply, then you get basically t size set 1 plus t size set 1 plus size set 0 times, this is like your complexity kinda. Recursive call, you recurse on this, and you can show t goes to n squared, but actually how do you see this? So there's actually like a nice representation with like a square, which I came across.
Isn't it n squared because of the very first like split?
Yeah, but how do you show that it's like, so it's a lower bound on n squared, yeah. But how do you show the upper bound n squared? This is like a square of side that, set 1, so this is a square. So in this picture, like areas represent number of operations, and then there's like a thing where like this area is like the number of operations of the multiply. So it's size of set 1 times size of set 2, and then you recurse and you kind of assume like inductively that this takes n squared and take this n squared. So it's squared plus size of naive FT, and the total area is n squared. And actually there's one more thing I want to say about this, which is there's this formula. X plus y choose 2 is x choose 2 plus y choose 2 plus xy. This is just like a formula this is just like knowledge you can know. You could work this out with like, you could like do the factorials to work it out and it's like fine. Or you can say like, this is like the total number of paths, because it's like you're choosing the 2 endpoints, but where could the endpoints be? They could either both be in here, so it's like size of set 1 choose, or size of set 0 choose 2, or the 2 endpoints could be in here, it's like size of 1 choose 2, or the 2 endpoints could split and it's like here, and it like splits it. And like that's, so there's like a formula there. Okay. Okay, so now there's, okay, now I'll go over the second problem.
some nice proofs.
So second problem is, again, given a 1e5 tree. Okay, the other thing I'll say about this is, like, if you're gonna cheese it with some n squared thing, the intended has to be like n root n, or like, okay, f of t over centroid's n log squared, but f of t is like a pretty big constant. Like, it has to be a pretty bad complexity to begin with for you to cheese it. But this is like, you can cheese it sometimes, but it's like, I don't know. It's like kind of risky. Okay. Node I has value AI. And there's an update. Well, let's do the query first. Find max value of given node U and ints L and R, find max value of a v for all v such that the dist of U to V is between LR. Okay. So this is the next problem. How are we doing?
Wait, can you repeat what it says after node U? It says query
Okay.
node U.
Yeah.
What is
You're given node U and you're given integers LR. So this is a query. A query is you're given these and you want to find the max value of a v, for v is a node, with distance between L and R from U. So it's like if you have a tree, it's like kind of like L and R, and you want to find the max of all nodes in like this range, kinda. And there's also an update. Given node U int x, you want to just set a U to x. Okay, so point updates and query. Okay, how do we do this? So you could attempt it with centroid decomp, and it would look something like this. We go to our model. This is like how I think about centroid. You have this like model. And let's try to maybe handle the query first. So like, let's say you're at like some node. Let's say this node is like here. Then like, you can get this like path length from U to the cent. Maybe this is like K. Oh, this is this is number of edges again. Okay, edges. And then the idea is that like you want to find the max L minus K to R minus K. And this will be like some range of depths. And you want to find the max over all nodes in like this range. And then similarly for the suffix, there's like some suffix of trees, and you want to find like, and the idea is that with centroid, it's like a node is in log n like decomposition. So like this kind of picture will only happen log times for this node. So you want to do this query like log times, and like I guess it's possible. I don't know. Maybe you guys think of a better solution, but it's like there's like children on the prefix of child 0 to I. This is like ith child. You want to query this like range, and maybe if this is negative, you like clamp it down to 0, and if this is more than the max depth, you clamp it. That's like fine. But like this is kind of the solution. You want to find a max, and it's like a 2D query, so you can do it, but it's like, and with updates, like you can do like, apparently like wavelet tree has like updates, so you can like do that. like point toggles. But that seems kind of tricky. Okay, let me show you a better solution. Okay. So we do edge centroid. And if you tried to do something like this, it would be basically n log cubed. I don't know, maybe there's a better solution with centroid, but you guys can let me know.
Like, because if the updates happen, like, doesn't that's because I'm assuming it's some sort of offline solution, right? So
You're running through all the queries and updates.
The way updates happen on a wavelet tree is kind of offline. We have to insert them all and then like toggle them on and off. But you basically loop through the queries kind of online-ish in order. I don't know. It might be doable in log cubed. It would be like tricky. Okay.
Wait, for that solution, are you like storing the actual decomps?
You would, yeah. And like loop over all decomps for a node in like log. You just like jump to them. This is like norm. So there's actually another. Let's go to the edge centroid model. It's in like this, and we get like U. And again, U is in log decomps. It's actually log like base 1.5n decomps, which is this is a worse log. I actually didn't mention this because it's like 1/3, 2/3. Worst case is you split 2/3 all the way, and it's like worse. But okay, but it's still log technically, so it's like good. And so the idea is that you have the same thing. This is like k. So we want to query some range L minus k, which is some range of nodes. We want to get a max in here. And the idea is that there's only two guys, so you just query the other guy. It's like the idea. And this is now just like a normal. You can just do a normal seg tree. You don't have to do any of this like 2D. You don't need any of this like 2D structure stuff. You just do a normal seg tree for each guy, and then yeah, max query, and you get basically n log 1.5 n log 2n. So because there's like log. This is the number of like decompositions with U in it, and then this is like the seg tree query. So you actually get a better complexity. That's what I wanted to show.
So how do you do the seg tree on that? Oh, just on like the number of data sets.
Just like for each decomposition, you have to like store a seg tree basically, which is like kind of a lot, but it's. And then updates, like you just kind of do the same thing. For each seg tree, you do a point update. The way I would implement this is kind of like you go to the BFS order. It's like 0, 1, 2, 3. You index them like this maybe. Nine, 10. And then you order like you do some like kind of like how HLD is like over DFS order. You do this over BFS order. Oh, this is like one way to do it maybe. You store a seg, just like your seg tree, and then you just do like seg tree index 11. You set to like x kinda. So like this is for the set. You loop over each decomp, and you just get the guy and you set it. So the update is also log squared. And yeah. The point is like it's a problem where like you get a better complexity. That was like the point. Okay.
So like like the class of divide and conquer problems where you like have queries where you're like counting stuff and you split by middle, then solve each like subarray and then split by middle. Can you like do like if you take one of those problems, right? Can you now solve that on a tree since you're effectively doing the same divide and conquer of like splitting into two halves? Like, because normally you might not be able to do that with central decomp since it's like you're splitting into multiple guys, but with this splitting like into strictly two things, like does Edge Centroid Decomp seem to like solve a more problems potentially than regular Centroid Decomp? Like I don't know, I'm like seeing a that might be like that could be solved.
Maybe, but you have to note that each node could be in multiple decomps, so it might get tricky. But like each like if it's like, I don't know, it might get tricky if you try to. But like the edges, if you like index the edges, it might work because the edges split and then.
So the edges are unique in each decomp, but the nodes.
Yes. Yes.
And I'm guessing that's where it gets its name.
I mean, yeah. There's actually a problem which you can solve with Centroid, but not Edge Centroid. Maybe I should go over that. It's called Seal and Commander, and it's like, I didn't actually prepare this, but it's like you want to assign a letter to, you're given a tree, you want to assign a letter to each node such that for any two nodes with the same letter, you want to have like at least one guy with higher letter. And you basically just do a centroid decomp and assign like the depth of the node. But that actually you cannot do with Edge Centroid. So it's like, Edge Centroid is not like holy grail because there exists at least one problem where you have to do regular Centroid. So I will mention that. But it's like, it's nice though, I don't know, it's like nice. Okay. Oh, there's actually, yeah, sorry.
In that problem, what would you say is that like, what would you say is the property of Edge Centroid Decomp that doesn't allow you to solve that problem? Just so like I can generalize it if I see.
Oh. It would,
You want it to split into multiple guys into that problem, for that problem?
that one's kind of like,
Wait, is it just the fact that the log is too big?
it's just that like the approach, like, I don't actually know. I don't know how to answer that
It's
actually.
like hard to generalize.
Yeah, it's just like that problem screams regular Centroid because you're splitting on the nodes. I don't know. I don't know how to answer that.
And maybe I missed this, but how do you account for in this problem
The single edges.
no, the nodes that are in like the same subtree? I think I just missed when you were talking about this.
Like for the query.
Yeah, for the query.
So like you like here's like a fact of Edge Centroid. Every path that has an endpoint in U will have the other endpoint will be in some decomposition on the other side. Like a path that goes like here down to there, who is all in this centroid, like there will be a smaller there will be a smaller decomp that has like where like this is one side and that's the other side, kinda. And so when you looped over this decomp, you would have handled it, and you don't like when you're in this decomp, you don't want to handle it, kinda, or is that?
Oh, so you actually do the decomp over the whole, like you do like a sub decomp as well.
Yeah.
Oh,
You split it into decomp, and then you like recursive. Like this is a tree, and you recursively. Yeah.
How do you handle this?
Yeah. So I'm about to get to that. That is actually a caveat. So this actually seems nice, but there's like single edge stuff, which I'll go over. Yeah. So there's actually a subproblem which actually makes so this is like the caveat to Edge Centroid, right? Is like you have to handle single edges separately. So the problem is like given update given node U and set a U to X and then query given node U, find the max of a V where dist UV is 1. So it's like you're given queries like find the max over all these, like all the neighbors. You want to find the max of their value in those updates. So this is actually a downside of Edge Centroid, which is you have to handle one edge separately. And in this problem, the one edge case is actually not trivial. Usually it's trivial, but in this case it's not. So it's actually Kind of annoying that you have to do this, but okay. The way to solve this is you basically root the tree, and then a node you basically say you have all its children, and you can like keep the values of their childs in like a set, basically. I think that's how you do it. It's like all the value, like a child 1, a child k. You keep these values in like a set, like std set or multi-set maybe, and then you can get like max value with dot rbegin, and then you handle the parent separately. And then updates, you basically say like you update this guy, and then you like not actually, wait, yeah.
Can you also do like the square solution where you have guys with degree vision and square? Like since you're already doing log squared, kind of.
You probably could. I actually didn't think about this. I'm pretty sure it's solvable actually. Because you could do like the BFS trick. Wait, how does this work?
The query is like query your child's set and your parent.
Yes.
Now you only need to update your parent's multi-set and you change.
Okay, that's what it is. Okay, yeah, thanks.
And then you can also do like, get all the nodes in BFS order, and then like all of your children are going to be adjacent in your BFS order. So you can second tree on that.
True. Okay, 2 solutions. Okay, so it is solvable.
What was it?
But it's like an.
Like you, whenever you want to know the answer for some node, you query its parent's value and like the max of its child multi-set. And then now the update is, you update some node, you need to set its, update its parent multi-set.
Oh yeah.
Your parent's
Yeah.
I think of them.
Yeah, that is what it was. That's what it was. Okay, or that solution. Yeah. So, but like this is, I mean, this is actually not too bad, but it's like you have to do it in addition, which is kind of annoying. Yeah.
So what's the reason why I have to do one or single
Yeah. So then it's like you have to think of like, okay, Edge Centroid is a way to handle all paths. This is like the way to identify the problem. It's like compute something over all paths, or do something for all paths. It's like boom, Edge Centroid, Edge. So then it's like, if like you want to handle paths that go like here, and you want to go through, like with at least one edge on each side. And then the idea is like, do you have to handle centroid? Do you have to handle paths that go from the cent to you? Well, the answer is no, because these will be in a smaller decomposition. Except for single edge paths, because when you like this guy will eventually have something that splits it, and you keep recursing down, and then like there will be like a single edge path, which will not be in a smaller decomposition, so you have to like do it outside, like separately. So that is kind of annoying, but okay. Yeah.
So like implementation wise, right? Like when you're doing centroid decomp, you have your like centroid decomp, find centroids, and then you have like kind of, at least the way I do it, I'm hoping that this is similar to, you have like a solve function for root, right? Like at least the way I do it is like you centroid, find your centroid that's solve, like there's a kind of sub problem you have to do of like given a specific root, calculate everything that goes through that root, right?
Yeah.
Does the only thing that changed, like, is the only thing that changes between the centroid decomp and the edge centroid decomp is that like solve function ID? Like you, like is that the only thing that changes?
Pretty much. Yeah. I mean, I didn't want to go into like code specifically, but yeah, there's like you can pass in like a lambda that like has like this the adjacency list and like it has the two sides, and it like removes edges as you go, so you don't have to like check anything. There's like a way to do that basically, but yeah, yeah. It's similar to Centroid, yeah, but yeah. Okay. One more problem? Okay, sure. Oh, actually, there's one more thing I want to say about this, which is that you want to, like, for a node, you want to loop over all the decompositions. So there's actually another downside of Edge Centroid, which is that how do you you have to index all, you want to like be able to index all the decompositions. And with Centroid, you can have the centroid be the index of the decomposition, because every decomposition will have a unique centroid, and there'll be exactly n decompositions, and it maps up 1-to-1, so it's actually nice. With Edge Centroid, like nodes are in multiples, so it doesn't work. So you have to come up with your own indexing for decompositions, and it's like a little bit more ugly, but that's like a separate minor detail. But yeah, okay. So then, okay. The final problem I have is find. This might be.
Can I get one?
Yeah.
I'm just curious about what you were saying a minute ago with looping over the decomps. Are you talking about specific to that problem? Like finding the max node in that range, max value?
There's other problems that you have to loop over each decomp for a node. There's that's a pretty common.
What's that?
For the updates.
Any problem where you can't do queries offline.
Yeah, thank you. Yes.
Well, my impression was for each centroid, you're effectively simulating all the queries in that subtree.
When you have updates, like they're doing it online with updates. So like every time you do an update, modifying each centroid that update is in.
So are you building a data structure on
The
current decomposition and then simulating the queries, or are you building full decomposition tree and then simulating all the decomps? Why do you have to do that?
you would have to store all the decomps, and you have to store the decomps in a way that you can, for a single node, you loop over the log decomps that it's in, and update this and query the seg tree. And then for an update, you loop over all log decomps that it's in and update its value in that seg tree.
I guess I don't understand why you have to.
It's kind of like you have
all the decomps instead of independently doing it for each decomp, sort of offline.
You can do offline if there's no updates.
Well, I guess
I was thinking you could do
you could
Yeah, you can.
Oh, you could over some over range and over time of update.
Over all the updates that take place in this subtree that affect these nodes.
Oh.
You would iterate through that, and then take a max over all the answers.
it's like kind of equally as annoying now.
You probably could do that
Why
actually.
is it more annoying?
It's like I don't think it's that much better. It's about the same.
Yeah, it's hard for me to tell. I just wanted to understand if it was possible to do it that way, I guess.
It might be
if you had to
possible.
do it.
Yeah, it might be possible.
Okay,
Oh dang.
sure.
I'm gonna go for an easier problem because we have less time. For each node U, this is gonna be a pretty simple one. Find the sum of dist UV for all other nodes V. Okay. This is actually not that hard of a problem. So for given a tree, maybe 2 times 10. For every node U, you want to find the sum of distances of all paths that have one endpoint at U. So this is V is 0 to n minus 1. And I guess I want to make a point with this problem, which is that you can solve this with reroute DP in ON. or you could do centroid. So reroute dp in on, or you could do either. You could also do centroid. Centroid, edge is optional. In and log. But what I want to say here is that the transitions are going to be easier with centroid, because if you've coded reroute dp, it's doable, but it's like, at least for me, it takes me a while to like think through the transitions. And if you're okay with having extra log, you can basically, I'll just go over this real quick. What you want to do is, like, for node u, you want to sum, and this is again k. You want to sum all the path lengths that start here and end somewhere here. And so it's like, what you want to do is like k times, this is like side 0, side 1, number of nodes in side 1, because you have each path has like this number of edges times the number of paths, which is the number of nodes in here, plus the sum, basically sum of path lengths, like sum of basically dist cent v. So like for all paths from cent to v, you want to sum the distance. It's like basically as you're DFSing in here, you just do like sum path dist of side 1 plus equal like depth is essentially what you want to do. It's like you're here at depth like 5 or something, or depth whatever, and you sum that depth into a count. It's an array of size 2, and then you just plug this guy in there, and then you just count like subtree size minus 1 for the cent. You don't want to count the cent, and that's what this is. So it's like, this is like your formula, and you do like result of u plus equals this. So like for node u, you just add this, and it's a solution to this. And my point is, like, this shouldn't be too bad, but my point is, like, this is a simpler transition than like what you would do with reroute. And so, because reroute, when you change the route, you have to like consider all this stuff that like goes outside. It's like doable, but it's, yeah. And there's like, I mean, this is just a simple example, but there's like harder problems where the reroute transitions get kind of crazy. And this stays pretty simple. That's like my point. And I think I'll end there.